Hi guys, welcome to this set of videos. What we're going to discuss here in this set of videos is going to be perpendicular lines. Again, we're sticking with this theme of angle relationships that are created by intersecting lines. And one of the most common kinds of intersections we run into in math is going to be when two lines intersect and form a 90-degree angle. We call those perpendicular lines. So that's why they're here in this chapter. Anytime you have two lines that intersect each other and those intersecting lines form a right angle, they're perpendicular lines. So all the way through this section here, our theme is really going to be, again, intersecting lines. That's the theme of the chapter, intersecting lines. But here in this section, we'll talk a little bit about perpendicular intersections, to be more specific. So, our essential question. What is it that we need to be able to answer by the time we get to the end of this set of videos? Well, what we'd like you to do is be able to tell me what are the key ideas about perpendicular bisectors of a segment. So we're going to talk a lot about perpendicular bisectors and kind of go over what all that is. But in order for you to be able to tell me what the key ideas are, we need to talk about the key ideas. So our objectives going to be to prove and use theorems about perpendicular bisectors and right angles. As we talk about these theorems, postulates, and perpendicular bisectors, right? Then you could use those to let me know what are the key ideas about perpendicular bisectors. So let's just jump right into this. Here it is, our theorem on perpendicular bisectors. Right? Here's what the theorem says. If a point, any point, pick, right, it'll be a point. Generally the point will be given to you, but if it isn't, you could pick your own point. If a point is on the perpendicular bisector, so if you have a perpendicular bisector, all right, and a point that's on it, that perpendicular bisector, right, of a segment, then it is equidistant from the endpoints of the segment. Very, very simple. I've got a diagram right here for you. Let me show you exactly what this theorem is saying. It's not that tricky. Here's what it's saying. I have a segment AB. Segment AB. What I've done, if I've split segment AB with line M. Please notice line M is a perpendicular bisector. First, why is line M perpendicular? Well, I show you right here in the diagram. That little symbol in there, that little box tells you it's a right angle. Anytime you have an intersection between lines and they form a right angle, that is our definition of perpendicular. Now, we know that M is perpendicular, but what makes it a bisector? Well, if you go all the way back to chapter 1, we talked about bisectors, and what we said is that a bisector will split a segment into two equal or congruent parts, which is exactly what those little hash marks tell me. Right there, I've got those little hash marks in red. I got one right there, and I got one right there. What do those hash marks tell you? Well, they tell you that this distance right here and this distance right here is the same. It's congruent. They're equal, right? That's our definition of a bisector. If you have a line that splits a segment into two equal pieces, then it's a bisector. So line M is a perpendicular bisector because it splits it into two equal pieces and it's perpendicular. It forms a right angle. Now here's what the theorem says. If you have a perpendicular bisector, and we do, we have a perpendicular bisector, pick any point you want to. I've picked a point for you. That point right there, point P. Right? Point P, here's what the theorem says. Point P is equidistant. Equidistant is just our way of saying in one word, equal distances, right, from the endpoints. Here's all this is saying. If you draw a line from point A to point P, and you draw a line from point B to point P, equidistant means that those two lines are equal. They're congruent. That's it, guys. That's all this theorem is saying. That's it. If you have a perpendicular bisector, then any point, pick any point you want to on the perpendicular bisector. I don't care what point you pick. Pick anyone that makes you happy. That point is going to be equidistant, the same distance from both of the endpoints. Guys, that's it. That's all it's saying. So let's go ahead and take a look at this then. Show you how this works. What I've got for you here is a triangle KLJ. KLJ. Here's what I've done. I have told you that KM is congruent to ML. So here's what you know. You know that segment KM is congruent to segment ML. They're congruent. How do you know that? The little hash marks in there, right? The little hash marks. And, well, it's perpendicular. So this tells me, right, because these guys are congruent, I know that M is the midpoint. N being the midpoint, that's a fancy way of saying it's a bisector. Right? M splits that segment in half. It splits it into two equal pieces. Now, the next part is, right, that little symbol in there tells me that M is perpendicular to KL. So I know that MJ, that segment, is our symbol for perpendicular, right? Perpendicular lines, you just draw a little 90-degree angle. Symbol for perpendicular is perpendicular to KL. What this tells me is that MJ is a perpendicular bisector. I know it's a bisector from this part right here. Those are congruent segments, so M must be the bisector. And MJ forms a right angle. That means it's perpendicular. So this segment, MJ, is a perpendicular bisector. So, what can I say about this triangle? Easy. Point J. Because J is on the perpendicular bisector, what do you know about those two distances? Yeah, thanks to our theorem, they have to be congruent. They have to be. That's the theorem, right? That's the perpendicular bisector theorem. It says if M is the midpoint and it's a perpendicular bisector, then any point on that line is equidistant from the endpoints. Equidistant meaning the distances are equal. All right, so that's the way that this perpendicular bisector theorem is going to work. Let's try a couple other problems. So here's what I've got for you. Right here on the next page, we're going to go ahead and do a couple of problems where I'm giving you some values and we got to figure this stuff out. Here's what we've got in the diagram, BD. So this line right here, BD, boom, BD. Now, I tell you BD is the perpendicular bisector. I'm telling you that. That's given to you. BD is a perpendicular bisector of AC. You could tell that from the diagram. Look, the little hash marks tell you those two segments are congruent and you got the little right angle symbol in there, right? So I wouldn't even have to tell you that. I give it to you in the diagram. You should be able to look at the diagram and be like, oh, look at that. BD, it's a perpendicular bisector. Splits it into two equal segments and it's perpendicular. It's 90 degrees. So it's a perpendicular bisector. Here we go. I want you to suppose ED is 16 centimeters. So ED, 16 centimeters. And DA is 20 centimeters. I want you to find DC. Careful, I gave you some, I don't want to call useless, but I gave you more information than you need, right? Look, the diagram tells you that is a perpendicular bisector. So thanks to our theorem, what do you know about point D? It's got to be equidistant from both of the endpoints. That means those two segments are congruent. If BD is the perpendicular bisector, then the distance from D to the endpoints must be the same. It's equidistant. Well, I know what AD is. I gave it to you. It's 20 centimeters. So here's what I know. Thanks to the theorem, I know that segment DA is congruent to segment DC. That's a terrible D. So, plug it in. DA, 20 centimeters. That's got to be equal to DC, which is exactly what I asked you to show. Okay, let's do another one. I want you to suppose EC is 15 centimeters, so that distance right there, 15 centimeters. And I want you to suppose that BA, that guy right, oh, sorry. Let's be BA, that guy right there, is 25 centimeters. Can you find me BC? Once again, hopefully you recognize it. I gave you some useless information. Who cares what the distance of EC is? It doesn't matter. I know this is a perpendicular bisector, which means point B is equidistant from both A and C. They have to be the same distance. That's what the theorem says. Well, since AB is 25, I know that BA is congruent to BC, and BA was 25 centimeters, so that must be the distance of BC. Alright guys, really simple idea here. This idea of a perpendicular bisector, just doing really easy problems. All you guys need to be able to do is just recognize it, right? And it should be easy to recognize. We put those little hash marks in there to tell you the segments are congruent, and you're looking for that little right triangle mark, or that 90-degree angle symbol to know that they're perpendicular. So really not too tough. All right, here's what we've got. Converse statement, right? We've been talking about converse statements, right? You switch the hypothesis and the conclusion. So we're going to do the converse of the perpendicular bisector theorem. Here's what it says. If a point is equidistant from the endpoints of a segment, then it lies on the perpendicular bisector. So here we go. I've given you a diagram. Right? Here's my diagram. I have this guy right here, BD, right? Let me do it in green. Here's what I know. I know BD, thanks to the diagram, is perpendicular. I have that right angle symbol in the diagram. So I know it makes a 90-degree angle. The question is it the perpendicular bisector? Well, according to the theorem, it is. Please notice the distance from D to A is congruent to the distance from D to C. The only way that can happen, thanks to the theorem, is if point D is on the perpendicular bisector. So here's what I have. I have AD is congruent to CD that tells me, therefore, BD is a perpendicular bisector. Remember that guy right there in green? That is our symbol. That's our symbol for perpendicular. So that means that BD is a perpendicular bisector. I know that thanks to this converse theorem. If those distances from any point to the endpoints are congruent, the theorem says it must be a perpendicular bisector. What does that tell me? Well, that tells me then that these two segments, that B is the perpendicular bisector. It bisects this into two congruent segments. Those have to be congruent. They have to be because of this converse theorem. So here's what I know. I know that AB is congruent to BC. Congruent to BC. Well, let's see here. What can we do? Check this out. I like this. This is a fantastic problem. I love this. Here's what I know. I know that AD, let's do it in, here I'll do it in green. AD is 10 inches. So this guy right here, AD, 10 inches. I tell you that BD, let's do it in red, BD is 6 inches. So this guy right here is 6 inches. Sorry, I know it's really small, but that distance is 6 inches. It's Pythagorean theorem. Right, I can use the Pythagorean theorem to find that third side. Okay, let's do it. A squared plus B squared is equal to C squared. Now, careful, what do I know? Right, am I solving for the hypotenuse? No, I was given the hypotenuse, so 10 will go in for C. Now, 6 is a leg. Does it matter if I plug it in for A or B? It doesn't. The legs are interchangeable, so it doesn't matter if I make A6 or if I make B6. It doesn't matter. Plug it into whichever one you want to. So we're going to go 6 squared plus B squared is equal to 10 squared. Well, that's pretty easy. 6 squared is 36. 10 squared is 100. B squared is going to be equal to, what do you get, 100 minus 36, 64, right? Yeah, 64. To solve for B, got to take the square root of both sides. What is the square root of 64? Yeah, 8. So what I found is that this guy right here is 8 inches. Now the question is that what I asked you for? Right? Did I ask you for AB? I didn't. I asked you to find AC, right? That's the distance from here to here. But I know that those two parts are congruent. So how do I find AC? Oh, that's easy. AC is equal, right, to 2 times AB. So AC is equal to 2 times 8, which means AC is equal to 16, right? All I have to do is double that distance. Since these two segments are congruent, double the distance and you've got AC, which turns out to be 16. All right, I got another one for you here. Let's do that one. Having a good time here with this perpendicular bisector theorem. Going well. Let me erase this stuff so we can do another problem. So this stuff doesn't get in my way. All right, here we go. Let me slide this up a little bit. All right, here's what I want you to do. I tell you that B and D, they're parallel lines. Let me go ahead and show that in my diagram. I know that these guys there and there, they're parallel. What else do I tell you? I tell you that C and E are parallel. Okay, I can do that. Boom, right, so all right, so there we go. I got parallel lines B and D, parallel lines C and E. Now, angle 1, 50 degrees. Angle 5, 90 degrees. I want you to find the measure of angle 4. Okay, here we go. Angle 1. Measure of angle 1. Right, again, going back to review what we've already done in this chapter, what is angle 1 congruent to? Well, we can say angle 1 is congruent to angle 2 thanks to, right, look, they're corresponding angles. They're both in the same position in different intersections. They're corresponding. Okay, let's keep going. Since I know the measure of angle 1, so 50 degrees is equal to the measure of angle 2. So there we go, now I know angle 2. Let's see, what else do I know? Oh, check this out, look at this. I know that the measure of angle 2 plus the measure of angle 6 plus the measure of angle 5 has to be 180 degrees. Right? That is a straight line. It's linear, which means 2 plus 6 plus 5 must be 180 degrees. It has to be. You guys plug in what you know. I know the measure of angle 2 is 50. I know the measure of angle 5 is 90. Plug and chug. 50 plus 90. Combine like terms. Measure of angle 6 plus 140 degrees equal to 180, which means the measure of angle 6 is going to be equal to 40 degrees. Okay, cool. Again, this is the angle addition postulate. Right, just simply use the angle addition postulate. The sum of all of the angles must equal the bigger angle, which is 180 degrees. And now, check this out. Please notice, angle 6 is congruent to angle 4. How do I know that? Do you see it? They're vertical angles. The measure of angle 6 is congruent to the measure of angle 4. They are vertical angles. So what does that mean? Well, since the measure of angle 6 was 40 degrees, that is the measure of angle 4, and we have just found what I asked you to find. Find the measure of angle 4. I did. It's 40 degrees. How did I do it? I used corresponding angles, I used the angle addition postulate, and I used vertical angles. Awesome. All my justifications for why I was able to do what I did to help me find the measure of angle 4. All right, guys, head on over to the next page of the notes. We'll just continue with this theme of perpendicular bisectors, as well as all the other stuff we've looked at so far in this chapter with intersecting lines. So I'll meet you on the next page.